Let's do this again now with a molecule called ethene. Ethene has a chemical formula that looks like this, which then could be drawn like this. Okay, just like that. We could even draw it maybe like this, CH2, CH2. We could also draw it with a zigzag that looks like this. All are representing ethene. So let's go and take just a look at the geometry of ethene. I'm going to add that double bond, change those to hydrogens, okay, and there we go. Now look at the shape of the molecule now. Do you see how it's completely flat? Well, we call that planar. This molecule is completely planar. So you can represent the molecule like this. Let's see, just like so. In the plane, like that. And the way I drew it on the left is 100% accurate because all the bonds are in the plane. But I could, in theory, take that molecule and rotate it like this. How would I represent that molecule on the left when I've oriented the molecule like that? Well, you have two hydrogens that are sticking towards you, and then two hydrogens that are sticking away from you. So we would represent it like this. Do you see how adding the wedges and the dashes don't change the molecule? It's just a different view. If I want to view it like this, then it would go back to the original. What if I drew it like this? If I drew it like that, how would we draw it? Well, we would draw it like this. I'm going to start over. It'd be more like that. And so we can get that arranged like so. All right, so being able to manipulate molecules in your head and on a piece of paper is a critical skill. So let's go back to now figuring out the orbitals that are used in ethene. So the first thing that we need to understand here is what is the hybridization state of that carbon. And when we take a look at that carbon, we see that there's one group, two group, three groups. So that means that carbon right there has to be sp2 hybridized. So if we go back to the basics, that carbon in the ground state, we have a 2s orbital and a 2p like this. There's the 4 valence electrons. And when we hybridize it to an sp2, what are we going to do? We're going to take 1s, 2 p's, and hybridize them. And so when we hybridize, those 3 orbitals are going to become degenerate. The same energy level, sp2, those 2 right there. But this one right there hasn't been hybridized. So it just goes on over to right here. And that is our p orbital. To be more exact, that is our 2p orbital. Okay? And now we fill in the 4 valence electrons all the way across like that. And so that would be our orange carbon, let's say. So sp2 carbon right there. What about this blue one right here? We're going to have the same thing as 1, 2, 3 groups around it. So it's going to be sp2 hybridized. It's also going to come with 4 valence electrons. And then we have our 4 hydrogens all coming with a 1s times 4. Okay? Now, let's figure out the orbitals that are used to form this bond here, or this molecule. Let's draw our carbon and our carbon right there. Well, let's draw our orange carbon first. Now, pay attention to the bond angles here. Let's zoom in here. What's the bond angle from there to there? That's going to be 120 degrees. What's the bond angle between the two hydrogens? That's also 120 degrees. And we saw from the picture, or from the program, that that orange carbon is trigonal planar. That's the molecular geometry. And so that's what I want to draw, is these three sp2 hybridized orbitals. Do I draw it like this? No, look at the model on the left there. Let's clean it up here. Okay, take a close look at the orange carbon. We have a bond here, here, and here, and they're 180 degrees from one another. So if I want to represent this bond right there, I'm going to have to draw it at that angle. So there's our sp2 hybridized orbital. This one right here would go there. And then this right there, okay, I'm going to represent with that. So those those three orange orbitals are sp2 hybridized orbitals, okay? And you have to think about that carbon in orange, that it's completely flat, okay? Now, if we do the same thing for the blue carbon, let's draw our blue carbon. It's going to have this one, and then right there, like this. And now what I'm going to do is just take these guys and, well, let's finish it off here. So this one, boom, this one, boom, this one, boom. For the orange, like that, okay? And I'm going to draw it like that because of certain rules about electrons. You can't have the same spin state in an orbital. Now look at what's going to happen. We are going to have head-to-head orbital overlap, like that. Okay, now what do we have? Head-to-head orbital overlap, which is used to form that sigma bond. So that is our sigma bond. That's sigma. And so we used this electron here and that electron there, because they're all right there. Okay. Now we know that we have 4 hydrogens. Okay. And so those 4 hydrogens are going to do what we've seen all along with ethane and methane. It's the same idea here. Okay. So what can we say about this interaction right there? Well, that's head-to-head. So that's going to be sigma. That's a sigma bond right there. And so all of these right here are sigma. And so we have accounted for all the electrons in the sp2 hybridized orbitals, and we've accounted for all 4 of the electrons from the hydrogens. But what do we still have going on here? We have an electron there and an electron there that we have not accounted for. And those electrons are in p orbitals. And so p orbitals are going to be perpendicular to the sp2 hybridized orbitals. So that means that let's see if we can look at it from this perspective here. Okay, so do you see here how I have the molecule completely flat like that? What you're going to have is orbitals above and below the plane. So what that is going to look like is if I draw the two carbons like this, and I'm not worrying about the sp2 hybridized orbitals, the p orbitals are going to be perpendicular to the sp2 hybridized orbitals. So envision, when we come back here, that those p orbitals are just on the top face and the bottom face of that molecule that I'm showing you on the right. But when we come back to this structure right here, the p orbitals that I want to draw in green now are going to be perpendicular to those sp2 hybridized orbitals. And so what is that going to look like? This p orbital that I'm going to draw is actually going to be sticking out at you. This lobe is going to be sticking out at you, and then this lobe is going to be sticking behind the sp2 hybridized orbitals. So it's going to be sticking out of the page and into the page. But that's very, very difficult to draw that. So we have to use our imagination here and realize that this p orbital that I'm drawing, and we have phase, that's perpendicular to the orange orbitals. And then this green p orbital right there is also perpendicular to the blue orbitals. Or said this way, above and below that plane. Okay, how many electrons come in this p orbital? Only one of them. And how many comes for this p orbital? Only one of them. And so now what we have is side to side orbital overlap. And that's going to be above and below this bonding axis. Right through there, that bonding axis, which is also represented here. I hate how this software does that. So the bonding axis is the plane that you see. Do you see how all the atoms are in the same plane? That's the plane, the bonding axis right there. And the p orbitals are perpendicular to that. And when they're perpendicular to that, and we have orbital interactions that are side to side, that is called a pi bond. That's our pi bond. And where's the pi bond in our structure here? It's right there. That's our pi bond. I would say that's our pi bond right there. So if I had two p orbitals and I wanted them to do head-to-head orbital overlap, it would look like this. Let's see here. There's a p orbital. There's a p orbital. Head-to-head orbital overlap would look like this. Well, let's give them their phases. Head-to-head orbital overlap would look like that. And then you see interactions right there. That would be head-to-head. Well, that's not what you see in our ethene molecule here. It's side to side. And your textbook shows this interaction right here in a different way, or they can use computer models to make it look a little bit more intuitive, I think. But being able to draw it yourself is super important. And so now we've accounted for these p electrons right here. So we've looked at all the electrons. They're all accounted for. They're all in orbitals. They all are used to assign bonding. So what we can say now is if we look at just a generic ethene right here, we can see that this bond right here, whoops, this one's sigma, 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 sigma. This one is pi. That's our pi. So how would we describe the bonding of, let's say, this right there? What orbitals are used to form that sigma bond? You would say, well, we have a carbon, this carbon, and that carbon is sp2 hybridized, which then is going to form a bond with a hydrogen, which comes with a 1s. Okay? So that's how you would describe the bonding for every single one of those carbon-hydrogen bonds. sp2 hybridized orbital with a 1s for the hydrogen. Now, how would you describe the bonding for this area between the two carbons? Well, that's going to have two components now. We're going to have the orange carbon right here that has a sp2 hybridized orbital. And then we're going to have the blue carbon that also has sp2 hybridized orbitals. And that interaction between the two is right there. But it also has a carbon-carbon pi bond. And so what are we using there? What orbitals are we using to form that pi bond right here? A 2p orbital and a 2p orbital. Or you could just get rid of the 2's and just say 2p orbitals on those carbons. And if we're going to keep the coloring code, that's our orange. And this would be our blue. Like that. So to describe the bonding of the carbon-carbon double bond, it's going to require two sets of data right there, because it has two different bonds. One is sigma, one is pi. The sigma bonds are created from this. So that would be our sigma. And this bond right here is going to be created from a pi bond. So that is the atomic orbitals in ethene, and that's how they're used to form these bonds.